Welcome to part one of case study ex3, where we'll show how to apply key operators from the Flux class in Project Reactor. These operators will be applied to create, reduce, multiply, and display big fraction objects asynchronously in a parallel thread pool. We'll also demonstrate some key mono operators as well. In addition, we'll take a look at some advanced error handling and exception handling operators defined in classes Flux and Mono. As always, you can find the source code that we're going to be analyzing in the rest of this video by clicking on the link below in my GitHub repository. We're now in my IntelliJ project for Flux case study ex3. Let's start off by taking a look at the ex3 class, which as usual provides the main entry point into this test program. As you can see, we have 5 methods under test in this program. We're going to take a look at the first 3 in part 1 of this video and then go through the other 2 in part 2. We'll start with test fraction exception 1. This tests Flux exception handling via the on-error resume and on-error stop operators using a synchronous Flux stream with asynchronously only appearing at the very end of the stream. Test fraction exception 2 will also test Flux exception handling, but this time we'll use the on-error continue operator using a synchronous Flux stream with asynchronously only occurring at the end of the stream. And then finally, we're going to take a look at test fraction exception 3. This will test mono exception handling via on-error resume and its operator using the asynchronous Flux stream and a pool of threads. As always, all 5 of these methods under test are registered with the async task barrier, and when the run tasks method is called, those tasks will run in the background, and the main thread, the calling thread, will block until the computations are done, and then we'll print the number of tests that completed successfully. So let's go ahead and take a look at the Flux EX class, which is where all the fun begins. We'll start by taking a quick look at the sRandom field, which is just a random number generator that's used to generate big fraction numerators and other values below. Let's start our discussion with test fraction exception 1. As usual, this creates a string buffer, and the string buffer is going to be used because we want to log the results from different threads. We don't want to have to worry about thread safety issues. We then define ourselves a list of denominators, which has 6 integers, the most interesting of which is the integer in location number 4 on the list, which is the value 0. You can only imagine the chaos that will ensue when we use 0 as a denominator. Let's now go ahead and take a look at how we're going to handle that condition with the local variable log exception and return empty flux. As the name suggests, this takes an exception. It's a function that takes an exception and returns a flux to a big fraction. The exception and its message is simply logged, and then we return the empty flux. And that will then indicate to Flux, to the Project Reactor Flux class and subsequent operators, to ignore everything from that point where the exception occurred to the end of the list or the end of the string. Let's now go ahead and see how we create the Flux stream here. We take our denominators list and we convert it into a Flux stream using the from iterable factor method operator. We then use the map transforming operator, which takes the denominator and uses it to create a random big fraction. We have a random numerator with the denominator that's passed in. All will go well until we reach that 0. And at that point, we're then going to get the arithmetic exception. When the arithmetic exception occurs, control will be transferred to the on-error resume operator. And that will catch the arithmetic expression, log it, and return the empty flux, as we saw up here. It just returns an empty flux, which basically means that anything from that point onwards will be ignored in the Flux stream. Now, because we end up using, or because the async task barrier framework calls on-error continue after it calls supplier get in order to invoke this operation that we're looking at, this method, we need to have the on-error stop method here. The on-error stop operator will prevent a downstream on-error continue operator from interfering with the calling to on-error resume above. Pretty subtle, pretty hard to understand if you don't realize the semantics, but once you understand it, it's easy to fix. Now, at this point, the values that were created, the big fractions that were created up to but not including where the exception occurred, will be collected into a mono to a list of big fractions. And of course, those will be the ones that got through before the exception came through and caused trouble. We then call the flat map operator on mono, and then we are going to sort and print the list. Now, sort and print list is a pretty cool little helper method that will sort the list parameter, the list of big fractions, in parallel using quicksort and heap sort. And it's going to run heap sort and quicksort in the parallel thread pool, which is gotten from calling the parallel factor method on the scheduler's utility class. So both those computations will run at the same time. And then whichever one finishes first will be taken by the call to mono first with signal. So whichever one finishes first will take its results. The other results will just be ignored. That computation won't be canceled. It'll just be ignored when they finish. And then we're going to go ahead and call the do on success action operator to display the list. And you can see display list just takes a sorted list. And for each fraction in the list, it goes ahead and it appends the mixed string to the string buffer. And then we display the results by converting the string buffer into a string. The last value that's returned from the end of sort and print list is a mono to void, or an empty mono that's called as a result of the then operator being invoked. So as you can see here, we end up getting the result coming back from flat map being a mono to void, which will then inform the async task barrier that this particular test method is finished, and it can shut itself down if all the other ones are done as well. Let's now go ahead and take a look at test fraction exception 2. As always, we use a string buffer to keep track of the intermediate results, so they're thread safe. As with before, we have a list of denominators, which, as is before, contains a 0 as the fourth value in the list. This time, however, when an exception occurs, we're going to use the on-error continue operator together with this by consumer called log error and continue. And that's precisely what it does. It's just going to go ahead and log the message from this particular exception of type throwable. And then the operations will continue in this processing other elements in the stream. We'll just ignore the one that had an error. Here's the way we create the stream. Parts of it look very familiar to what we did before. We use from iterable and that factor method operator to convert the denominator's list into a Flux stream of integers. We use the map transforming operator in order to be able to create a big fraction that has a random numerator and a denominator that came out of the stream. We use on-error continue, and on-error continue, as you recall, will log the error and continue. It doesn't stop, unlike on-error resume in conjunction with on-error stop that we saw in the previous test method we looked at. So only the particular value that threw an exception will be ignored. Everything else will be collected up into a list of fractions, which will be returned as a mono to the list of big fractions. We will then call the flat map operator on that, as we did before, and we will sort and print the list as we did before by using quicksort and using heap sort running in parallel. The third and final test operator or test method we're looking at here is called test fraction exception 3. And as you can see, it creates a string buffer. It's going to create a function error handler that looks similar to the one we used earlier when we were dealing with the on-error resume operator in the Flux class, except this time we're going to be using the on-error operator in the mono class. So as before, we log the message, and then now we're going to go ahead and convert the exception, whatever it was. In this case, it's arithmetic exception, of course, because we divided by 0. But we're going to convert that into the big fraction constant 0. And you'll see how that gets used in a second. So here's what the program looks like. It's a little different from the previous streams we saw, but has some of the same flavor. We start out by creating our denominators list, just like we did before, with the fourth element being a 0. We then take that denominators list and we create a flux of integers. So we have a flux stream of integers, except this time we're going to use flat map and the flat map concurrency idiom, which is a really cool idiom we've talked about in earlier parts of this lesson. So as you can see, for each denominator, we're going to go ahead and emit a random numerator with that denominator as a big fraction. And then we're going to schedule that to run in the parallel thread pool. And so as you can see here, subscribe on, as always, will cause this computation and then everything below to the end of the flat map inner publisher portion to run in different threads in the parallel thread pool. If something goes wrong, for example, if we divide by 0, that will trigger the error handler for the mono's on error resume operator, which, as we saw up above when we took a look at that, we'll just go ahead and return 0. So in this case, we're just going to return 0 if an exception occurs. Not the only way to handle it, perhaps not even the best way to handle it, but it's the way we're going to handle it for this test example. The next thing we do is we take everything that's not an error, and then we log the big fraction and the big reduced fraction we're going to use to multiply with. And the final operation that's part of this inner publisher form of the flat map concurrency idiom is going to go ahead and multiply the big fraction by the big reduced fraction. And that will end up generating the results. Now, all that will go on in parallel, and the final thread to go through and do the final processing in that pool of threads will then come out, and it'll call the rest of the operations from here to the end of the outer Flux stream. So what it'll do is it'll take a look at every one of the big fractions that comes through, and it'll filter out anything that's less than or equal to 0. So if a big fraction is less than or equal to 0, it's going to be ignored in the rest of the processing. We then take all the results, except of course for the one that generated the divide by 0 exception. We collect that up into a mono to a list of big fractions. And as before, we use flat map and the sort and print list helper method to go out and sort and print that list in parallel using quicksort and heap sort. So now that we've walked through the code, let's go ahead and run the code and see what the results are. And they're quite interesting. Now we're going to ignore the results for the final two methods. We'll talk about those in part 2 of the lesson. But what we're going to talk about here are the results from test fraction exception 1, test fraction exception 2, and test fraction exception 3. Now you can see in this case, test fraction exception 1, that's the one where it had a divide by 0 and it used on error resume and on error stop. And you can see after the first 3 elements, we stop because the 4th element was the 0. So everything from there on is ignored. For test fraction exception 2, that's where we used on error continue. And in that case, we only ignore the one where the divide by 0 occurs, but the other 5 come through with flying colors. Then in the third test fraction exception 3 case, we always get the processing done because we're going to convert exceptions into the value 0. So you can see in this log output that we get a 0 here, but then we filter out anything that was less than or equal to 0. So the final results that we sort and print are actually going to exclude any values that are zeros. So those are the results from running the first 3 methods under test for case study ex3. We'll look at the other 2 in part 2 of this video.